This video will discuss polynomial zeros. So in this video, we're going to let f of x be a polynomial, which in general has this form, an times x to the n, plus more terms, a1 x to the first, plus a0. Here, these coefficients, an minus 1 down to a0 are real numbers, and we're going to say that this first coefficient is not 0, so that this is a degree n polynomial. To be clear what I mean by a 0, I'm going to say that a 0 is a number c such that if I plug in c into my function, get out 0. So here are two observations about zeros of polynomial equations. If n is odd, then f of x has a real 0. I think I made this observation in a previous video. The idea comes from understanding the basic shape of polynomial functions and their graphs. So if I have an odd polynomial and a polynomial of odd degree, then the graph might look something like this. It starts down here way below the x-axis at negative infinity. It comes up, it wiggles around a bunch of times, and then it heads towards positive infinity. Because I'm starting down here at a big negative number, I'm going up here to a big positive number, there must be at least one place where I cross the x-axis, and that's the 0. There are no jumps or gaps in the polynomial, so this 0 must exist. Maybe as a generalization of this simple observation, I could say that if I plug in a number a to my function and I get out a positive value, and if I plug in a number b into the equation and get a negative value, then I know my function must have a c between a and b such that c is a 0. F of c is equal to 0. This is a refinement of the idea in property 1 because the picture looks like this. Here's the interval from a to b. I'm saying, though, that if you plug in a to the function, you get out a positive. If you plug in b to the function, you get out a negative. So somewhere in the middle, you must cross the x-axis. So there's my c value. Now, in general, if you have a large degree polynomial like degree 20, it's exceedingly challenging to find an exact formula for a 0. If you have a degree 2 polynomial, you can use the quadratic equation. And there's a similar but messier equation for degree 3 and maybe 4. But once you get to degree 5 and up, especially if you're degree 30 or 40, it's exceedingly challenging to find an exact formula for any 0. However, you can use this property too to pin down narrow windows where zeros must exist. I want to show you that with this example. So let's find the 0 for, how about the function f of x is equal to 3x to the fourth minus x minus 1. The idea is I'm going to essentially guess a couple of values to test what's happening with the function. Maybe I'll plug in 0 just as a random guess. So if I plug in 0 for x, I get negative 1. And let's try another value. A simple one is positive 1. So if I plug in positive 1, I get 3 minus 2, which is positive 1. So that means there must be a 0 between 0 and 1. So if I'm here on my number line, here's 0, here's 1. The function is negative on one endpoint, positive on the other, So somewhere in between, I have my answer. Now, I'll refine my guess. I know I have to have a 0 in here somewhere, so why don't I split the interval right in half, test that value, and see if it's positive or it's negative. So if I plug in 1/2 or 0.5, I calculated ahead of making this video that you'll get a number that's approximately negative 1.3. So I'm still negative over here. I'm still negative at 1/2. So now I'll plug in 0.75. If I plug in 0.75, I will get negative 0.8. So I'm still negative over here. Let's try 0.9. So if I plug in 0.9, I get 0.06, a small positive number. So at 0.9, I'm positive. So that means there must be a 0 between 0.75 and 0.9. So there is a 0 between 0.75 and 0.9. If I need even more accuracy, I can repeat this process. I can test more values in the small window that I've narrowed down the availability of a 0 and get better and better approximations. Now, this seems like a relatively simple idea. It is, but even this idea is powerful enough to be used by many computer algebra systems to check where there's zeros. So even though this is a simple idea, it is sometimes used in computer software. Okay, wonderful.